Okay, so for this Module 2 quick self-check, I will display the answers and then I'll come back and discuss each one in order. So the first one has an answer of C, 2 is C, 3 is B, 4 is B, 5 is x as a function of t is equal to negative dt cubed over 6 plus 4t. 6 is D, 7 is B, 8 is B, and 9 is C, and then 10 for the open response description of the motion. It's headed to the left the entire time, and then from 0 to 2 seconds, it has a constant speed, then it slows down, then constant speed again, and then it speeds back up. All right, so let's go ahead and review each of these. So for this first one, I'm actually going to talk about what the motion in each graph corresponds to as a way to kind of further understand and test your understanding of graphical understanding of motion. So in this one, we were told a couple things. We were told that there was a positive constant acceleration, and we were told that the initial direction of motion is negative. So positive constant acceleration means our acceleration is bigger than 0. An initial direction of motion, that's our velocity. Our initial velocity is less than 0. So what we expect is that because we're headed in the negative direction to start, because our velocity is negative, and the acceleration is positive, we need to be slowing down to start. So let's just look at each graph and see what we can do. So we'll start with A. Well, A is one, remember here that the slope of a position versus time graph, which is what these are, is equal to the velocity. So this here has a constant velocity. So that means this is what an acceleration equals 0 graph would look like, which is not a positive constant acceleration. So we know that A is incorrect. B has an initial velocity, the slope of the line is negative. So we do have V naught is less than 0. But as time goes on, V naught, the slope of the line, is becoming more steep. That means that it's speeding up. So that means that the acceleration also is negative because the velocity and the acceleration line up. And when velocity and acceleration line up, then something speeds up. So this would be something that has an initial direction of motion negative and maybe a positive negative constant acceleration. So that does not fit our description of motion either. C does, as we know, and so if we look at Y, the initial slope is negative, so we know that V naught is less than 0, and it's shallowing out, right? So the slope is becoming more shallow, and eventually it actually comes to instantaneous stop. So it is slowing down, which means that our acceleration is opposite our initial velocity. It actually slows down to a stop and then starts speeding up in the positive direction. And that's okay because that wasn't precluded from any of our descriptions here. So it does eventually turn around, but initially the velocity is negative and the acceleration is positive. And then for D, we can actually see right away it's not initially headed in the negative direction. Instead, its initial slope is positive, and then it's speeding up. So this would be something that has initial velocity greater than 0, and it's speeding up, so its acceleration lines up with its initial velocity. Okay, let's move on to 2. So 2 is a person stands at the edge of a cliff. They're gonna throw one ball straight up in the air, and it's going to come and hit the ground below. And then they're going to throw another ball straight down with that same initial speed. So this question has everything to do with the symmetry in motion. If I throw a ball up at 10 meters per second and it goes up in the air, when it comes back to the level of my hand, its speed is again 10 meters per second. So in this case, when the ball goes up in the air and then comes back down, they're going to have the same speed when it gets to that same level of the cliff as it had on the way up. So another way to kind of draw this is if I say I throw something up and I give it some initial speed v sub I, then the final velocity v final would be equal to negative v sub I. There's that symmetry. So there's nothing then different between the case where I threw the ball up, but then by the time it gets to the cliff and then it comes down, it has that same speed, and the one where I just threw it down with that speed to begin with. It's not talking about how long they were in the air. Obviously, the one I throw up in the air is going to be in the air longer. It's asking which one hits the ground at the greater speed. And the one that is thrown downward has the same speed as the one that would go up and then come back down. So they would have the same speed at the ground because of symmetry. All right, number 3, you can use the 4 kinematics equations that we used in free fall to analyze absolutely any motion, including non-constant acceleration. And this is absolutely false. For non-constant acceleration, we have to use calculus. Those 4 equations, the ones that are commonly used, for analyzing free fall or projectile motion, are assuming constant acceleration. So those assume, and they were derived, if you remember the video, those assume constant acceleration. So you have to use calculus if you have non-constant acceleration. All right, number 4, if you drop an object in the absence of air resistance, it accelerates downward at 9.8 meters per second squared. If instead you throw it downwards, the magnitude of its acceleration after release, meaning after you let it go, well, it hasn't changed. It's always going to still be 9.8 meters per second squared. That is what free fall is. That is our only thing that we have, which is the acceleration due to gravity is 9.8 meters per second squared. And this is after it's been released. Whether or not it's already headed downward or whether or not you drop it from rest, it does not impact the acceleration. It only impacts your initial velocity. All right, so for number 5, say the acceleration versus time is given by this function, and it's a function of time, so we know we have to use calculus. I'm going to go ahead and erase the answer so that I have space to work. And I want to write the position as a function of time. I just have to integrate twice and be careful about my initial conditions. So I know that my velocity will be equal to the integral of my acceleration, so negative dt, and then dt, negative capital dt. And so that's going to equal negative dt squared over 2, just integrating that term. And it's an indefinite integral, so plus c. Now I'm going to call this C1 because we're going to integrate twice, so we're going to have 2 constants of integration. So C1 here is going to be my constant of integration, and because v at t equals 0 is 4 meters per second, so v of 0 equals 4 meters per second. So if I plug in 0 to my equation for v, for t, at t equals 0, plug in for v, then I find that C1 equals 4 meters per second. So I can then write v as a function of t equals negative dt squared over 2 plus 4. And now I'm ready to move on and find my position. So x as a function of t is then the integral of v dt. And so I'm going to then say that's equal to negative dt cubed over 6 plus 4t. See how I have to keep the constant of integration in, and then that's now my new velocity function. I integrate that. And then I have plus c2. Now, because it started at the origin, then that tells me that at t equals 0, x equals 0. So C2 is just 0. So my final answer is, in fact, for x as a function of t, negative dt cubed over 6 plus 4t. Okay, so number 6, it's asking for the solution to problem 8, which was the one with the air cannon. You had to use calculus in the air cannon, and then you had a free fall problem with constant acceleration outside of it. It's one of these combined concept problems. We had to integrate the acceleration in the cannon in order to get the velocity of the ball just as it left the cannon. And then we use that velocity as the initial velocity for our free fall portion. So D is the correct answer for 6. For 7, say that you throw a bowling ball and a ping pong ball and you give them the same initial speed upwards. Which one goes the highest if we ignore air resistance? Well, I gave them the initial speed. I gave them the same initial speed. Their acceleration is the same because it's both free fall when we ignore air resistance. So negative 9.8 meters per second squared. And so they're going to go to the same height. Nothing we've done has involved mass at all so far. We won't get to things involving mass until we start talking about forces. All right, almost done. Number 8, the velocity graph shown. So that means that this is velocity as a function of time. And we're assuming one-dimensional motion. Where would the object have to start its motion in order to end up at x equals 4 meters at the end at t equals 8 seconds? So for this problem, don't think that you have to calculate it in these bits and make it this really tedious thing. Whenever you're given a graph, try to decide whether it's the slope or the area that is useful to you. In this particular case, the area of this graph, the area of a velocity versus time is going to be the same as the integral of v dt, right? And the integral of v dt is going to give you your displacement, delta x. So in this graph, the area gives me my displacement. So all I have to do is say, okay, here my area would go from 2 to 4, so that'd be 2 times 1. That would be plus 2 meters. And then this area for the negative portion, this area would be 2 times negative 2, so minus 4 meters. So my total displacement from this motion is going to be negative 2 meters, which means that if I want to end up at 4 meters, then I need to start at 6 meters because I'm going to have a displacement of negative 2 meters. So for any graph that you have to interpret and get like numbers out of, think, do I need the slope or do I need the area? Areas are integrals and slopes are derivatives. Okay, so now we have this situation that we're looking at the same graph except for now let's say it's an acceleration versus time graph. So we have to interpret this very differently. And we initially have an object moving in one dimension. It's initially headed towards the left with the initial speed of 10 meters per second. And that's going to be important. We'll see why. Which is false? So first, just a tip on these multiple choice type questions. Sometimes it can be confusing, especially when you're looking for a false statement. Label everything as true or false, and then go back at the end and then see what the question was asking. And that way you can not get into some sort of careless mistakes that might come up with these sorts of wordings. So the object is moving faster at t equals 8 than it is at t equals 0. So again, this is a graph. We can think what's useful about it. The area would be the integral, areas are integrals, of the acceleration dt. That's my velocity. So that's going to be my change in my velocity. So now we know that my change in my velocity is going to be equal to, and I'm going to add, it's headed in the negative direction, negative 2 meters per second. Not per second squared, just per second. I was initially already headed to the left. And so that means I'm still going to be headed to the left and I'm speeding up. So the object is, in fact, moving faster at 8 seconds than it was at 0 seconds because I have more negative acceleration. So what's going to happen is if I'm headed to the left, my v initial is less than 0. So in this portion, I'm going to slow down. And I'm going to slow down by the amount of that area. I'm going to slow down by 2 times 1. So by 2 meters per second. And then here, I'm going to speed up by 4 meters per second because it's to the left. So the object is moving faster. I'm headed to the left, but my speed is larger. So A is a true statement. And again, just labeling them true or false and then go back and answer at the end. The object is still moving towards the left at t equals 8 seconds. Yes, it is. That is a true statement because I started at 10 meters per second. And because when I slowed down, I only slowed down by 2 meters per second. I didn't come to a stop. So I'm always headed to the left. And then C, I have C marked as the one that is false. So let's see why. The object is instantaneously at rest at some moment in time shown. And that again is false for that same reason. I started at 10 meters per second to the left. I only slowed down by 2 meters per second, and then I sped up again. So at no point was my velocity 0. And then D, the object was slowing down at 3 seconds. Yes, because my initial velocity was negative and this acceleration is positive, then I am going to be slowing down. So that would be a true statement. And so therefore E, more than 1 is false, is incorrect. And so that leaves C as the correct and only correct answer. And so then we basically answered 10 by just analyzing this motion. First of all, we've decided that it never changes its direction of motion, so that it's headed to the left the entire time. During this motion here, I'm going to get rid of some of these highlighting so that I can go ahead and mark on it. So in the initial time, its acceleration is 0. Doesn't mean its velocity is 0. It just means it's moving with a constant speed. Then the acceleration is opposite our velocity, so it slows down. Then again, acceleration is 0, constant speed. And then I have a negative acceleration and a negative velocity, so I speed up. All right, so let me know if you have any questions at all before you finish out Module 2 and take the Module 2 quiz.